Hello and welcome to our Diffpoints tool demo. Diffpoints are a special type of breakpoint that captures snapshots of variable state over time and automatically diffs those snapshots for you. In this video, we will show you our Diffpoints IntelliJ IDEA plugin for Java. We will work on a maze solver Java project by Debug and Isdemir. It is a small open source project that visualizes a couple of different search algorithms. We modified its code a little to introduce a logger, but while doing that, we introduced a bug. So let's see how we can use Diffpoints to debug it. First, let's run the program. We can open a sample maze. And first we can look into, for example, the A* search algorithm. And we can see how it nicely visualizes finding the path and backtracking it. Next, let's clear the results and let's run the depth first search algorithm. Immediately we can see that there is something wrong with it. So let's open the algorithms class and let's look through the DFS algorithm implementation here. First, we see variable declarations for previous nodes, which are used for path backtracking, a node stack for the iterative implementation of DFS, and a couple of helper variables. Then we can see the while loop that runs until the stack is empty. First, the loop pops the next node, the topmost one, since this is depth first search, and then it checks whether we reach the end or whether the current node was already processed. In that case, we are skipping the node. Next, the DFS visits the node by setting its color, and then it looks into its neighbors. For each neighbor, it checks whether it was searched or not, and if it wasn't searched, first, if it doesn't have yet previous node set, it will set the current node as a previous node. And then, if it was not searched again, it will push the node on top of the stack. After setting up the neighbors, it just logs what's going to be the next node and the end of the loop. And after the loop, it checks whether a path was found and it prints it out or visualizes it again. At first glance, everything looks correct. So let's start debugging. We already have the Diffpoints plugin installed, so we can open the Diffpoints tool window, going through View, Tool Windows, and here Diffpoints. Here in this view, we will see the snapshots captured by the tool. Since the loop is the core of the algorithm, let's see what happens inside it. To observe changes between loop iterations, we can use a line diffpoint. A line diffpoint is designed to compare variable states at the same line of code when the line is reached multiple times, making it ideal for examining loop behavior. So let's place a line diffpoint at the start of our loop. So let's see here. So we can right-click the gutter and select line diffpoint from the context menu. Before we continue debugging, I would like to highlight some line diffpoint settings. So let's right-click the line diffpoint, and here we see the settings. What I wanted to highlight is the save behavior. We have 4 different options here. We can either keep save all, which captures and keeps every snapshot. We can use save last end states, which keeps only the last end snapshots in memory. We can compare first state against the most recent state, or we can just select which iterations we are interested in. For our case, I think keeping only the last, let's say, 3 states is the best option. That should provide enough context without cluttering the UI. Let's click done, and we should be ready to go. Now we can run the program in the debug mode. We can again load the sample maze, and we can run the DFS algorithm. So at the first stop, here we see what we would expect. The current node is empty. We see the start node, and we see that the nodes themselves contain the start node. Let's skip to the second iteration, as this will become more interesting. And let's look a bit closer what we can see here. So here we can see 5 things highlighted: start, nodes, element counting nodes, mod counting nodes, visited. So these blue highlights are highlighting the changes. So the start node changed, which seems a bit suspicious. What's going on? Let's take a look. By expanding, we can see that what changed was just the node color, which is correct. It was marked as a visited node, so we can rule this out probably. Then we can look at the nodes, and we can see that the node that was the only node put in the node stack now became the current node. This is highlighted by green because before it was null, now it was set to the start node. So we can see that this changed because the first node was popped and then it was replaced by this one. Then there was another node added, so these should be the neighbors. And we can already see that there is something suspicious about this, because if you look at the starting node here, it has left, bottom, and right nodes as its neighbors, so at least 3 available neighbors. But here are only 2, so it looks like there is something wrong with neighbors method. We can also see that visited count changed, but that's expected. We visited one node in one iteration. Let's run one more iteration just to see what happens. So, okay, so here we have the 3 iterations next to each other. Now when I'm looking at it, I think we only need the last 2, so we can manually hide iteration 1. And we can compare just iteration 2 and 3. As you can see, it's automatically updated highlighting based on the current diff. So what we're interested now is like how the node stack changed. So we can see that the bottom one stayed the same and this one changed. So node that was put to current one, it's the latest topmost one. That by looking at the X and Y position, we can see that it increased the Y position compared to the starting node. So it's this bottom neighbor. This bottom neighbor should have 2 unvisited neighbors, one to the left, one to the right. Yet we see that only a single node was added. So this confirms that there is something wrong with the neighbors. So let's stop this debugging session for now. We discovered that something is wrong inside the loop, specifically around pushing the neighbors on top of the stack. To pinpoint the issue, let's add a few group diff points to the loop body. So first, remove the line diff point, we don't need it anymore. And now let's talk a bit about the group diff points. A group diff point is the second type of a diff point. It allows us to compare variable states across 2 or more different lines of code, which makes it perfect for this case. We want to compare the state between multiple lines of code in the single iteration of a loop. So let's add the group diff point to every interesting line in the loop body. So let's start at the beginning. Then one before visiting, one after visiting, one right after neighbors generation, and last one at the very end of the loop. Before running the program again, I would like to highlight the settings of the diff point once again. So let's quickly look at the settings of this diff point. Here what's interesting is you can set groups to group diff points. Each group diff points are only compared against the group diff points in the same group, so we can have different comparisons based on what you need. In our case, we can keep them all in group 1 as it's a single group, and we care about the snapshots of all the snapshots inside a single iteration. So now let's run the program again and open the maze again, run the depth first search algorithm, and now skip all the snapshots until the very end of the loop. In this case, let's hide this so we see better. So in this case, we only care about changes to the nodes, as we know this is what we care about. So let's expand this and let's see the nodes here. So at the first diff point at the beginning, there's a single node there, is the start node. Then after we pop it on the next step, there is no element node. That's correct. Then after marking it, nothing changes. Again, correct, maybe. Then after adding the neighbors, we can see that there are 1, 2, 3 neighbors. One to the left, down, and to the right, which matches the maze. So it is correct. So after adding the neighbors, everything looks correct. And then at the end of the loop, the topmost one is missing. And this confirms that adding the nodes here, this code here is correct. And something breaks the loop here in the logging code. So let's quickly look into the next DFS, as this seems to be the culprit. Oh, and here on line 72, we can see that when we are trying to look at the topmost node, instead of peeking, we popped. So let's rerun the program and see whether this fixes the issue. Again, open the maze and run it. Oh, and we can see it's working now as we want it to work. Perfect. We are able to identify and fix the issue. And that's it. Using Diffpoints, we are able to quickly narrow the problem down from the entire DFS implementation to a single line of code. Instead of manually tracking variable values across iterations and trying to remember what changed, Diffpoints automatically captured the relevant states and highlighted the differences for us. Line Diffpoints helped us understand the behavior of the loop over time, while group Diffpoints allowed us to follow state changes through the different parts of the algorithm. We hope Diffpoints can make debugging complex state changes faster and easier in your own projects. Thanks for watching.